Welcome back to the Cernbert Show. This is probably the last recording of Cernbert before he is yanked off the air next week. But as my guest this week, we have Philbert. So this is going to be a fabulous way to go out, Phil.
One way or the other. Yeah, one way or the other.
Yeah. And I would say that this is what happens when the adults leave the room and leave the kids in charge.
That's right.
Herbert may never take another vacation after this experience, but we're all looking forward to having him back next week, and certainly next week with being Tesla's earnings week, that'll be an exciting week. But
By the way, every single week ends up like this.
Yeah,
like every week, like we're like next week, there'll be nothing on deck, and then all of a sudden, bam!
It's amazing how much is going on with Tesla.
Yeah, exactly.
And then after earnings, we've got the annual meeting. And then we have a few more things to look forward to as far as robotaxi deployments and Optimus reveal and things like that. So yeah, should be an exciting fourth quarter.
Yep, never ends. That's good.
Yeah. Well, we've got a few things to talk about today, Phil. And one of the things that I wanted you to talk about was your post titled "The Magic of Tesla FSD." And amazingly, now you're up to part 8 on this. This is an incredible series of posts, and this is the Optimus edition. And Optimus is near and dear to my heart because I believe that it is really the future of Tesla. And Elon, I think, has said as much recently, where he said something like it'd be about 80% of the value of the company ultimately.
Yep. Agree.
So perhaps you can begin walking us through this presentation.
Well, the premise here is about unification of the technical architectures of both of these products. How that feeds in, and what's happened here, perhaps from an engineering perspective, like a program perspective, and then where this tech has such great similarities. The AI of Optimus, the AI of FSD are actually way more similar than different. But to the average person perceiving it, they would think, oh my God, these are, one's a humanoid robot, one's a vehicle. How do they even marry? So today, what I want to do is kind of walk through it in as much gory detail as we can go through, to show that not only is it becoming unified, and I say becoming because I think it isn't unified, it's becoming unified. What are the pros and cons to that for Tesla and each of these programs? Because I think we have to consider these things as distinct separate programs who have different endpoints that affect the entire business model of their respective areas. And it's not just Tesla's an engineering forward company, but that said, because of that, we kind of lose sight of the fact that there's so many other moving parts that happen that you can't just pretend everything is an engineering project there. Because then, if you put out a cybercab, you have to consider the entire service chain of that and all the other aspects, right? Put out Optimus, you have the same problems with Optimus. What do you do? Do you rent them by the hour? Do you replace them when something breaks? How does that work? How do you create that supply chain for that? So engineering is one part of it, but it always becomes the central focus of because Tesla is an engineering forward company. Its leader brings us there, and so it's fun to talk about.
Absolutely. So let's jump to this slide. If you could just take us through what you're displaying here.
Yeah, so I did slides. I took a cue from Cernbert, made sure that I had slides available. Herbert likes them, and you usually have them, so I decided we need to have them.
I appreciate that.
Yeah. Okay. So I want to talk about 6 different areas where FSD and Optimus AI is unified, and or has a chance to be unified, and how I see it progressing. And those are data formats, the data pipeline, the simulator, how learning works in terms of how they're training the AI, the architecture of that trained AI, and then the endpoint of this, which is inference, meaning what's the runtime? How do they look the same on vehicle or inside Optimus? So that's the 6 areas that I see where we have the opportunity to have this unified architecture. So
at first blush, Phil, this chart looks the same in both columns except for the first area, the data
Yeah,
format. Everything else here looks very similar.
yeah, and I think it is. I mean, obviously, the devil's in the details, and there's a lot of nuance to each of the specifics, and we'll talk about that as we run forward in this. But what I'm really trying to present in the first area about data format is, to me, the data format, the so-called data set, is a unified temporal object. It's basically a bunch of time series data. It is a mix of the data that is coming from the cameras. In the case of FSD, it's 8 360-degree view. In the case of Optimus, it's two forward, rumored to be or thought to be one rear camera, and then the only really add would be touch sensor data from Optimus. But the way the viewer should think of this is that it's a unified data set architect. It's a data set, and it has this data layered in it, and it's temporal data, so it's time sequenced, and it's a capture. Really, what drives it probably is a frame rate, right? A frame rate from the so-called eyes or the cameras. There's a certain number of frames per data set object. And then all of their data is layered in there with appropriate timestamps. So, for example, you might have a frame rate running at, say, 30 frames a second or 60 frames a second. That's packed in here. You may do 6 frames, right? And then, but maybe you're getting IMU, the inertial management unit for roll pitch yaw. Maybe you're getting that data, at 120 hertz. So you're going to have more
Hmm.
little samples of that potentially, or they might throw them out. And ultimately, what we have this thing that I'm calling a data set that I think has the same kind of compression format across both types of devices. Yes, you can pack different data as per this description here, but ultimately, when you unpack this thing and you send it down the data pipeline, which is the next topic, it's all the same.
Could the traction control system and the input from that be considered to be touch for the vehicle? Is that one
Yeah,
way
I
to
think.
sort of think about that?
Well, I think I've grossly simplified this because I think there are other data inputs from the vehicle that I'm certainly not putting here.
Oh,
Remember, one thing that's really important to understand, that there is, because we're sort of running this feedback. In other words, the outputs of one thing become kind of the inputs again, and you don't see that occurring. But that's probably because it's more of a current neural network component. Like it's feeding back into the neural network as a hidden layer that you never see. It's not really part of it. So when you think of an AI, you think about the inputs to the AI, and we're thinking about sensor inputs here principally, right? And there are other sensors. To your point, there are other sensors that may or may not be packed in there. I mean, if
mhm.
you think about, the vehicle has hundreds of different telemetry data points
Yeah.
that could be provided in that temporal data set, right? There's hundreds of things. When I was at Rivian, we probably selected for telemetry set maybe 200 to 300 outbound telemetry data points, and we internally had thousands of native data signals that told us all sorts of things about tire pressures and temperatures, and you can imagine. So the real answer is, as much as they need, that they would put in that data set.
Okay.
So I think we should jump to the next slide, because I think it starts to sort of already talking it. So really, what most of this conversation has been about, the device data, which is the far left box here. It talks about Optimus and about vehicle. And the point is that I'm saying that is a unified data set. There is a very direct format to that data set. Maybe different data's in there, but it's all time series data. It's packed in. It's probably largely driven by the camera frame rate. Okay.
Just
As we
before you
run,
leave we leave
yeah,
this box, Phil, for the car, it's pretty obvious how you get the data, right? You drive it around.
yeah.
For Optimus, what is the optimal way of obtaining all the data that Tesla needs?
Well, I mean, in terms of its sensors, it's just providing the data at time points, regardless of its inherent motion, right? I mean, if it's just sitting still, it still can be providing its GPS position. It still provides what it's seeing. It doesn't have. There's no necessary dynamics of the object itself to still be recording data, right? So, what is the IMU showing you in terms of roll pitch yaw when it's literally just standing? Well, it's the same value as the last time, as the last time, as the last time.
Yeah.
But
Uh,
all
uh,
that's important. All that's important.
Sorry, my question was more about getting the volume of data, I guess, that
Oh,
Tesla needs, right? In order to get the volume of data that Tesla needed to train FSD, they had the FSD beta
oh,
program.
yeah, yeah, yeah.
Does that then follow that we need to have a bot beta program? Is that how you think Tesla will approach this?
No, I mean, I think they definitely have. There's a difference here, clearly, right? I think though, what started to change that is the next kind of column of thing here, which is the simulator itself,
Hmm.
because what we now have the opportunity to do is produce synthetic data. So, in a case of Optimus could theoretically train off of just raw video data. That's like watching a human do certain aspects of motion, like loading a dishwasher or whatever. But more than likely, what's happening here is that yes, there'll be some kind of environment data collection, whether it's a beta program or not. I think is see. I think maybe the point I want to make about Optimus, sort of a meta point, is that when Optimus is delivered, it will be a version one product, and it will have a certain amount of what we would say action capability and cognitive capability.
Hmm.
And I think we can't see it as like the perfect delivered product on day one. It's going to be able to do a certain number of tasks. And that's why I think it will largely start at manufacturing and service and layer and eventually work itself into the home, because I don't think it will have all the nuance necessary to find itself in the home environment with all its necessary cognitive components, et cetera. So I think in the beginning, so this brings in the question is like, can you effectively make the product better over time? The answer is absolutely. That's the cool thing about this. It's like that is why you need to spend a lot of time on getting your actuators right. You got to get your hands, you got to get the hand. Elon's been focusing a lot on the hands in the version 3 Optimus. And there's a good reason for that, because those are the fixed elements that you can't really easily swap out or change. But what you can do is swap out and change the software continuously through over the air updates. So what I think we'll end up with is an Optimus version 1 that has a set of capabilities that we could put on a chart, and it will probably do a lot of things at first, and then as soon as you jump in and you look at it, you'll go, "Oh boy, there's a lot of things it doesn't do. Oh my God, it got a version update." It's sort of like FSD. Like, consider FSD version 14. For the first time, it's starting to navigate parking garages and gates. And it's starting to park, the so-called last mile aspects of it are starting to be addressed.
Hmm.
That is not true in version 13. We lasted an entire year in the market, principally an entire year in the market with version 13, and only when it was delivered to us did we realize, oh, there are still things that have to be added to this thing. There's still a bunch of features that make it a complete stack. And I think that will be exactly true of Optimus. We'll see it released into the real world, and that real world could be inside Tesla manufacturing, could be at SpaceX, it could be at third parties, and it will start to do its thing. And then all of a sudden, it'll get an update, and it will have more action skills and more cognitive skills as time goes. And part of that will be data collection, to your point.
It's interesting when I think about the data, right? You think about an AI model like ChatGPT, right? A large language model or Grok. It's trained on words. It's trained on what humans say, right, or
Right,
what we've written. But what Tesla's doing here is the data is what the world actually looks like.
right.
It's so different in so many ways, and it seems like this ultimately is so much more important. What's the
Um,
right way to sort of think about the differences in the types of data, the written word, the spoken word versus what the world actually looks like?
yeah, it's a great question, and I just popped out an article about a week ago on that very subject, which talks about FSD data alone. I
Yeah.
just focused on the data aspects, and exactly to your point, I was dialing into the collection of real world data not interpreted by a human in the loop,
Yeah.
like removing the human from the loop. Like right now, what we have when we train an LM is we're basically taking, we're compressing the hell out of data, which is we are taking data from the real world that has gone through a human brain, it becomes written word. It's not only compressed, but it's also selected, right? So it's like, what do you want to say? What didn't you say? And then it goes into this so-called, let's call it a let's call it a database, for lack of better definition, that now has all this knowledge, and we think of it as, oh, that must be the sum of all knowledge. And the answer, of course, it isn't, because if you just look in the real world and you look at all, just take vision data alone, any given time, we are able to perceive things in the, or not just we, I mean, a robot, whether it's a vehicle or Optimus, are able to perceive things that the human has never ever recorded. There's never been a recording of that information. And the other part is that you can now, with these systems, do it at a scale that humans could never come together and do, right? So
Mhm.
if you just think about research projects where you have like a PhD thesis and someone's gathering data, they may have an army of 30 people go out and do some primary research about the natural world or something. Imagine an army of Optimus bots in the millions looking at the same problem with a much quicker, you know, ability to perceive, and then a way to collect the data and an aggregation that's never been done before. So, I mean, we call this box real world data, and what we would say about it, I think, most importantly, is that it removes the human from the loop. So, in a way, it allows an intelligence to develop in parallel or side by side with the human intelligence. Like right now, what we think of it is, we're like, oh, it's human intelligence, and we're trying to teach a system how to be intelligent like a human. But what if you don't think of it that way? You think of it as, we're trying to teach a system intelligence. It's like we could factor that out and say, we're trying to teach a system how a dog thinks. Well, we're trying to teach the system how a human thinks. There's not much difference in that, right?
Right.
I mean, there's levels, but
Yeah.
now we're in a circumstance where we can let the system teach itself to build its own primary first principles intelligence. And I think that's ultimately what will happen and evolve here, mostly through data collection.
You,
Yeah.
you made a comment in one of your posts that really struck me. You said to reach AGI, AI must learn from non-human data, right?
Yeah.
So large language models are fundamentally then limited by the data that goes in, which is human-generated data.
Yeah.
But what we're talking about here for Tesla with FSD, with the bot, is these systems can collect non-human data.
Right.
So do you think that
Yeah.
this is an important component in order to get to AGI? This is the missing piece?
As I said, I think we have a weird way of defining I mean, some people have a weird way of defining AGI. It just means that it's better than a human by some definition, right?
Yeah.
But so a good way to think about it is, to be better than a human, you have to essentially remove the human from the loop. And therefore, that's, I think, how you ultimately build a system like this. Because we built, for example, a bunch of models in physics, which are all human. I mean, it comes from the brains of Newton and Einstein and all these other famous physicists. And that's just a human model on some real world physics, which could be very close to truth, or it could be very far from the truth of the real world. So what we'll have in the future is the ability to have systems that examine the real world environment on their own and come to their own conclusions, that sometimes are insights. If you think about some of the stuff that Einstein, it's very insight based,
Mhm.
which we don't really know how insights occur, but some of it is just data based. Like, it's just formed by gross amounts of data. Like, extreme amount of data can inform a system of things that seem like, what is intelligence at some level? Like, we often think, if you have a person that has a near photographic memory, they are viewed as intelligent by many. But those people may lack these other attributes of insight and common sense that we can't quite put our finger on. But we know one thing, that robots, whether they're vehicle robots or they're humanoid robots, have access to more inbound data than a human by far, can process, can ingest. And one needs to think about it as not just about the single unit, it's about the aggregation.
Mhm.
Like in human knowledge, aggregation is about dissemination to a large group of humans, right? Like, oh, now we all know about Einstein's relativity. ideas. Well, if certain people don't rate it, it's not known. But that's not true with a network. Like this should be seen as any of these devices know essentially everything the other device knows.
Yep.
So you get mass input aggregation, and you also get mass knowledge or second derivative dissemination because you've essentially got a network of devices. Yeah, it's cool stuff.
Absolutely. So if we move to the simulated data column, I'm sort of curious as to, when you think of humans, when humans dream, is that our kind of simulation data that we're running through in our brains? That's kind of one thought to pull on. And then the other thought is, what's kind of the optimal ratio between data to data collected in the real world on device
Mm-hmm.
versus simulation? Is it 80/20? Is it 99/1? Is there a, a desirable ratio there?
Well, I mean, one thing I'd like to say about this is that I think simulation is based on template, and template is already data that's collected in the real world, you know. So in other words, when I talk about it in the article, I talk about simulated data, I'm talking about essentially Tesla being able to pull data sets from well-known nameable intersections, you know, like Third and Market in San Francisco, and then remove from that template of streets various elements, right? Be able to really kind of break it down to all its elements and say, okay, well, let's first remove all the vehicles and the pedestrians and the bikes and so forth. And now, when we're starting to build a simulated or a synthetic sample, let's change the configuration of that template. We have a template. Let's layer on that template an extreme number of pedestrians walking through the intersection in very random ways, not following the rules. Let's add vehicles that do things that we could never record a vehicle doing, right? I mean, or we'd be lucky to record a vehicle. Like, how would how would the system react if a vehicle jumps over and comes into the oncoming lane, right? We may not have a natural sample for that anywhere in the Tesla data set, although they probably do. So the simulator allows them to essentially layer that in. So I think it's sort of like you start with this template, and then you can now augment it to create realities that are hard to have captured in the real world. And that's, I think, the first element of it. Ultimately, this simulator that they built is, let's say, it's a physics real simulator, so it is attempting to get very close to what would be the real physics. In other words, the thing that actually would be recorded off the vehicle is indistinguishable from the object that's synthetically built. Like if you saw it, you shouldn't be able to tell the difference. You're like, I'm not sure, I can't tell. But they're using the simulator in three areas of this entire pipeline. So let's back up one step and say, what is a pipeline? A pipeline is really about how the data moves through the system. And in this case, what we're talking about is really starting with the device data, running it through a whole bunch of steps, and outputting neural network models that then move to the car, right? That's kind of like the two pin ends here.
Yep.
And in between, we have the simulator, pre-processing, storage, and training. The simulator, though, gets, it's this particular diagram isn't as complete as I'd like it to be. The simulator gets purposed in three different areas. It creates synthetic data, which is sort of the input I'm showing here. Like it along with data that's captured in real world, we can create now synthetic data. But it also gets used to run the training and reinforcement learning, sorry, which we can talk about in a bit. And then it also gets used for validation as well. So we can run scenarios through. I mean, part of training an AI is validation, but if you want to think of it from a much simpler point of view, how might Tesla take a given release of FSD and test it? Now, we often think, well, the way that happens is they distribute it to a bunch of people in the real world, first employees that are, focused on testing, maybe the robotaxi network itself that as it currently exists with the safety observers, and then ultimately select groups of building number of users. But the reality is probably before any of that is done, it's run through a simulator. It's run through something that is actually running the inference in real time
Hmm.
and making the determinations of whether the outcomes of have met the desired goals, right? In terms of fluidity of driving and obviously safety of driving, right? So where were we? Yeah.
Well, yeah, we're maybe getting off track a little bit. But this one question, and maybe this isn't the right time to ask it, but the one thing that comes to mind for me is how close can Tesla get between this simulation and reality, right? How tight can those two worlds be? Can Tesla close the loop fast enough so that the fleet is basically training AI as it drives? Like how close can we get to that kind of state?
Well, that's a great question, and I mean today, let's be clear what's happening. This what I'm presenting here on this slide is all happening at the data center
Yeah.
effectively. I mean, obviously the data is drawn in from devices and it targets a model, on the devices. But today, on those devices, the data, let's not say devices, let's just say on the vehicle for the sake of FSD, that model when it's executed, the inference of what we call inference. It's 100% read only. There's no, it's not learning a damn thing from your
Yeah.
behavior. It's not learning anything from your behavior. Now you might say, well, wait a minute, that's not true. What if FSD allowed me to pick a preferred parking spot or or navigate this particular gated entrance in a certain way? In my mind, all that is an input preference. It's just part of the input context window of a set of preferences that may run through the read-only neural net system. So would the system want to train dynamically, like learn, like a lot of people out there report, oh, I've run this street 50 times and I've done it this way. And all of a sudden I found my FSD to operate that way. And I'd say, bullshit, that's not happening. Like that is not happening at all. I mean, it's nice to think it's happening, but it's not happening. And by the way, is it even desirable? Because what Tesla can't have, they can't have, let's be certain about this. They can't have a system that is non-deterministic from a corporate point of view,
Yeah.
right? They can't say, oh, Phil's system behaved this way because Phil trained it in this particular way, and CERN trained his system this way. And so where's ground truth? How do we know what we're liable for versus what you've done to your system? So ultimately, I think the answer to the question is it's really more about data selection as it's always been and bringing it back and training the model in a centralized way. What Tesla has the opportunity to do, which we'll talk about in two more slides, is how they can apply sort of your preferences on top of the stack to make it feel very personal, to make it feel like it's your thing. Like same thing with Optimus. Optimus, when you have Optimus at some level, it will develop what we would effectively call a personality, right?
Yeah.
And it will have to preserve what that nature of that personality is, independent of software updates coming from Tesla, right? We can't be in a position where we have a we have an Optimus in the home. It becomes familiar to us. It understands us. It remembers what we say. It develops a personality that we want it to develop. Now, I don't want to. When I say personality, I don't want to think. Don't go so far as to think total human personality trait, like an independent kind of like that Optimus would be different. But there will be differences because it will have understood the data from your home
Is
and the things you want it to do. And it must remember that box of things separate from the model updates that come from Tesla, right?
is a way to think about that is perhaps what we're seeing right now with FSD, where we've got hurry, chill, sloth, and now Mad Max mode. Are those modes personalities, or is that the wrong way to think about it?
Yeah, I think they're just moded inputs. I think they're just basically they're sending a desired kind of it's really just a desired preference. It's like a dial, like if you think about what's going in, what's part of the input. Well, we talked about some stuff in the previous slide. We said we got camera data, we got the IMU and the GPS and a bunch of potentially other signals. Well, other things that might go in there are those types of preferences. Like I want the car to do this. Some of them are routing preferences really that you should pull out of the AI. Like if I said only take 280 and don't take 101 when I go to the airport, that's not related to FSD, right?
Yep.
That's just a routing preference through the
Yep.
nav system. And then the FSD becomes a slave to the nav system, right? And in fact, that's an input too, right? The nav
Yep.
system itself is like where it's supposed to go is really directed by the nav system as a kind of higher, like the puppeteer of FSD. Um, so I think things like those modings that you see are really just kind of an input that tells it to tighten its tolerances here or loosen its tolerances here. So, like for example, if it's effectively saying, "Oh, I need this is not code," so we could be a little careful, but we need to describe it maybe like code. I need this kind of I need this much offset in order to start braking, or I need this much offset before I come in on a lane for a car that's in the adjacent lane. Imagine you just tighten those offset numbers and push them as parameters through the system.
Yeah.
Now all of a sudden it becomes tighter and tighter and tighter. And I feel like really honestly they don't even need to mode it with these like they've got these discrete modes from sloth to Mad Max. Honestly, I think it could just be a dial that's just kind of turned up. And I think there's multiple levels of parameters that are associated with each of those levels. So some of them might be about stopping distance offset. Some might be about how it perceives how how much time it needs before the light goes from green to amber to decide whether it runs through the intersection or not. All
Yep.
the little decisions that we make as humans about how cautious or lack thereof we are in our own driving, and those are multitudes of things. So I don't think it's a single input. It's probably 50 or 60 little things that go into to give it a personality.
Are there any examples you can think of for FSD that you would say is personality? Is it perhaps the way that it allows other vehicles that are trying to change lanes and it'll give way to that vehicle?
Yeah, well,
I think
I think these driving modes are the best examples
okay.
of its personality today. Would it exhibit more in the future? Yeah, but they might be seen more as like more or less kind of straight up preferences. Like I want my car only to park in spots where there are no adjacent vehicles or corner spots in a parking lot. Like go ahead and spend your time running around the parking lot until you find that corner spot.
Yeah.
Or and from you might say, well, a human that does that with their Ferrari or something, that's a personality trait of how they want to be. So I think that there's a little bit of a blur of line of preference to personality, but
Yeah.
definitely there's a lot more potential inputs that the human can have in terms of preferences that don't affect the ultimate model itself, the model still being read only. Yeah.
I love how in your post you draw the line between imitation learning, right, which is what I would say is where FSD learns by copying humans,
Yeah.
right?
Yeah.
And reinforcement learning, which is where it learns by improving on
Yeah.
humans.
Yeah.
I think that's a interesting way to think about that. If you could just kind of expand on that a little bit.
Yeah. So, I mean, when we think about these neural networks that are built, they what at some raw level, they're these layers of things that ultimately have these things we call parameters, and they're numbers that get set, right? And the question is, how do you set them? How do you get them set? And there's sort of two general modes of operation, at least the ones we should be talking about here: imitation learning and reinforcement learning. So, in imitation learning, what we're doing is we're taking actual data samples, and by the way, possibly those built by the simulator itself, right?
Mhm.
And we are sort of imitating the best behaviors, right? We're not trying to imitate poor behaviors. We're trying to imitate. So there's a process you can see in the pre-processing step here I call auto labeling, and the purpose behind that is to say, oh, a data set comes in and it's labeled as to its sort of utility in the system. Like, does it reach, like, is this a first question is a good sample? Like, have we selected something useful? Well, if the sample just shows the car, crashing into another vehicle, and some it was based on somebody's poor driving decision. Well, that's not what we're training the system on. We could train that system on that, and we could have vehicles that just crash into other vehicles all day long. But when we say that we're trying to build a system here that's better than human, we're really talking about the average human, because what in imitation learning, at least, we're selecting to the far right of that sample set. We're selecting the best human drivers, right? And there's details of how they're doing it, but the point is that's what they're doing. That's imitation learning. And the problem with imitation learning is effectively that it really doesn't get better than the best human. It doesn't really get better than the best human because it's just basically taking, I mean, you could say, well, the simulator adds a lot of value there in doing certain things that would show vehicle trajectories that are awesome, preferred. But that's the next box, which is reinforcement learning. And so what reinforcement learning does is it kind of turns it around a little bit, and it says, well, you know what we're going to do? Instead of having a driving sample that determines, like, imagine a scenario where you're trying to have Tesla, the vehicle, avoid hitting a pedestrian that dashes out into the road from a hidden spot, like a vehicle. Now, how do you do that? Well, you could train it on an imitation learning basis, but you may never have the raw sample to deal. I mean, that would
Yep.
be a terrible sample to have because it might include hitting the pedestrian, right? So what you can do is you can say, well, wait a minute, what's the rules of the road here? No pun intended. Well, we don't want to hit a pedestrian. We sort of don't want to be rear-ended because that could put the driver at risk of the so-called passenger at the FSD, the driver, and it also could put the driver and passengers in the car behind it at risk. We also don't want it to make incredibly weird lane changes because we could sideswipe another vehicle without a lot of caution. Now, how do you determine what the best thing to do is when there's no perfect answer, right? Well, avoiding hitting another human being head on, from car to human is probably the thing you want to avoid the most. Then you want to maybe mitigate. The second order thing is to mitigate the rear end collision that could happen because you're trying to create that avoidance. And then the third level thing is, well, you don't really want to hit a car in an adjacent lane, but if you do, you're going almost the same speed. So you're just talking about material body damage and not necessarily,
Mhm.
human damage. So what you do in reinforcement learning is you apply what you might call awards or penalties to the different scenarios, and then you set the system up again using the simulator to run hundreds or thousands of different what we call trajectories, and each of them run through and accumulate their appropriate award or penalty. And the system learns of the ones with awarded behavior are the ones that are preserved in the neural network, and the ones that have the highest degree of penalty are excluded from the training of the neural network. So, what we do with reinforcement learning is we effectively create a circumstance where we now have a lot more training samples that go beyond the human. We are essentially removing the human from the loop again, and we're moving past what any rational set of samples could ever have produced for us, whether they're simulated or not. And in a way, what's happening, the cool thing about reinforcement learning and the dovetail back into this Optimus thing is that, well, we need to jump a slide or two to get into what I think the cool realization of this is. Yeah, this is largely it. What's cool about this is what we're saying is, like, what is the ultimate neural net architecture that comes out of FSD training or Optimus training? And my claim is that they're really very, very similar. And the way they're similar is that they have two big halves of them. The first half is they have this thing called the perception area of the neural network. That is about perceiving objects in the scene, right? Static objects and dynamic objects. And in a sense, there's no real difference between FSD and Optimus, right?
Right.
In other words, a vehicle looks at an intersection and it sees other vehicles and stop signs and it labels these things as, well, there's an object, we'll label it as a stop sign, and it's static, doesn't move. Stop sign doesn't move. There's a traffic light over here. There's this other sign. Oh, there's a human. Okay, that's a human. It's got sort of a movement vector, like we can see it going across the intersection in successive frames. So I've excluded the perception side from this diagram, and I focused on the planning side, which is where it gets interesting. Because I mean, years ago, perception was super interesting because it was really hard to do by code. It was really hard to like look at just a 2D pixel and say, well, what's in that thing? Like imagine writing the piece of code to try to figure out what's in the picture,
Right.
whether it's Optimus taking a picture of your kitchen or FSD taking a picture of your intersection. Now a neural net can do that like amazingly well. One of the classic amazing things that neural networks can do is really do this dynamic and very accurate perception. The second part of FSD, or frankly Optimus, is the action component, which is the planning block. I call them the planning block. This is, because in classic self-driving, it's always been described as perception and planning. When we think about planning, we have to think about it like this isn't something like someone sits down and writes the ultimate plan. This is something that's happening 30 times a second in the car. It's planning its next output, which is controls, right? So what we have at the core is we have data coming in that's basically camera data and other data we've discussed. And on the other side of this, we've got control. So in the case of FSD, those controls are accelerator pedal, brake pedal, and steering angle, right? Those are really the principal things. I mean, you could say blinkers and horn, but those are kind of ancillary things. And what we're doing in these planning blocks, again, these are all neural networks, there's no code here, is we're determining what to do, what control values. In the case of Optimus, the control values are much richer. We've got all the movements of all the actuators, hands, arms, the head rotation, the hip rotation, the legs, the joints, much like a human. Those are all the kind of control actuators. What's really cool here, and I think where they've unified this architecture, is they've taken two things. They've taken a heavy dose of reinforcement learning. In other words, I think what's happening inside Tesla AI is that they are leaning heavily on reinforcement learning, both for Optimus and for FSD.
Mm-hmm.
And so they're creating these scenarios, these multiple trajectory reward penalty scenarios, and they're ending up with good training from that. And what they're doing is they're building these little expert blocks that do specific things. And in the grand scheme of things, AI people would call this a mixture of experts architecture, right? These expert blocks have a certain say in the output of the controls. So if you look at the one in the example here I have for the vehicle, I show that there are two expert blocks. I actually show four, and I show urban intersection expert. That's the one that knows how to get through an intersection without hitting another car or person. And then I have another one, which is a wet weather expert, like snow or wet weather expert, right? Very different thing, right?
Mm-hmm.
But each of them have some certain, and what happens in these mixture of expert architectures is that they come in, the data comes in, and it goes through this first component called a router. And the router determines which experts to pick and which ones to shut off and make dark. So if you see in my example, expert 3 and expert 4 are like shut down. And what might they be? Well, maybe expert 3 is highway driving expert, but you're not on a highway, you're in an intersection. And maybe expert 4 is a sun glare expert, but there's no sun or glare because we're in the middle of a rainstorm. So those guys get turned off by the router, and other guys get turned on. And when I say they get turned on, they get turned on by a weighting. Like how important is so you notice, and I say 79% important for the intersection expert and 21% importance related to the wet weather expert. And they blend those two together. So what might that be? Well, the most important thing is to explain how should the car navigate the intersection. But maybe the wet weather expert comes in and says, yeah, but you're going too fast.
Right.
Like you could lose traction. So we need to dial back And maybe, by the way, that informs whether it should run that yellow or not, to be fair,
Yeah,
right? Like, oh,
that's right.
the intersection expert says go for it, and the weather expert at 20% value says not so fast, and it comes down to a decision, which is it holds.
Or the
Okay.
weather expert says, "Well, there's not enough stopping distance. I can't brake in time."
Yeah,
Yeah,
exactly. Yeah.
go
So,
ahead. Yeah,
but it doesn't. It only has so much weight into the
yeah,
transaction. It may have more. I'm just making an example here.
yeah.
Now, an
Is
Optimus,
Phil, real quick, is that decision making process, that routing part of it, I guess?
yeah,
How frequently is that being determined? Is that multiple times a second that
yeah,
decision's
yeah.
being made?
It's in line with the same inter inference rate.
Yeah. Okay.
So, it's a magic box that's doing some of, like, incredible stuff about
Yeah.
picking these little experts. Now, let's take a look at Optimus. Optimus, I have this two experts. I made these up. The pick and place small object expert, and then I have the balance expert, where balance is like, okay, well, maybe the thing is moving a dish from the sink into the dishwasher, and there it's leaning on the pick and place expert. For small object, like one hand, let's call it one-handed expert or something like that, right? Um, the other thing is, well, the bot can't fall over while it's doing this, so the balance expert has to be in there to make sure that it's inputting the IMU data to keep the thing stable, right? As it moves, it can't tilt over or fall. And if you kind of run the logic here, these experts, when they get smaller and smaller in scope, like what they do, let's call them something else. Let's call them skills. So that gets really cool. Like, we've suddenly collapsed this idea of this, technically based mixture of expert architecture to really like a mixture of skills architecture and sub skills within that. And so that you can imagine that with Optimus, it's a little bit more fine grained. There's a lot more discrete skills. But in a sense, my argument is that they're just part of these blocks for experts, if that makes sense.
So what you're telling us is that this same neural architecture is controlling a car, a humanoid, and probably something else, anything else, right? Tesla's building one intelligence here, right?
Yeah,
That just happens to live in different forms, like,
yeah,
the same brain operating in multiple bodies.
yeah. And
That's where we're
eventually,
that's where we're headed, right? It's one intelligence, one,
yeah,
not FSD per se, but just a brain. A
100%. The total endpoint of the unified architecture is that effectively the same brain or downloadable model in FSD or Optimus is it's the same. It's
So
the
with
same.
every improvement in FSD, is that directly at this point helping Optimus, or are you
No,
saying perhaps at this point
no.
they're not unified?
No, they're not unified at this. Remember, in a sense, they're never unified at some of these skills, right?
Yeah.
To a certain extent, because, like, you don't need the intersection expert in Optimus, or maybe you do.
Sometimes you might, and same thing with the
Like,
snowy
if Optimus
weather
is
expert.
riding a bicycle through an intersection,
Yeah.
okay, just saying.
Yep.
But, I mean, we if we're taking it to the extreme, the answer is they're the same. Where are they today? I think where they are today, and note the slide's title, architecture. It's not about necessarily what's in the boxes now. It's
Yeah.
about how the boxes are set up. And so what I'm saying is, essentially, what you've got a reinforcement learning technique building these expert blocks or skills that, in driving, we can see how they manifest as
Yeah.
per this diagram, and in Optimus we can see how they manifest.
So you could easily add a third item here, like a drone, let's say,
Yep, yep,
and it would be the
absolutely.
same architecture.
Yeah, it would, I mean, really, maybe the biggest takeaway is that these are real world AI systems that are principally visual sensor systems that are the inputs, to a certain extent, right? I mean, like, the big fat part of the data is visual data, and that's true of
Yeah.
humans as well, right? I mean, we most of our data is coming through our eyes, and, hearing, and then,
Yeah.
taste, and so forth, you know, but ultimately, yes, that's the truth. Yeah.
So an Optimus with wheels, you're saying, is a future product category.
Yeah, wouldn't that be interesting, right?
Flying cars, flying
Well, I
robots.
mean, the weird reality of this is, will Optimus be able to drive any car?
Yeah.
Of course. When when it finally reaches the endpoint of its existence, it can get in your dad's old Chevy Tahoe and take it for a run.
Until then, though, it makes sense to have the car be the robot that drives itself rather than put Optimus. But you're right. If you put Optimus on a tractor or some other car that's not that doesn't have FSD in it, in theory, it should be able to drive it.
Yeah, of course, and that's
Yeah.
when we see these things merge,
Yeah.
which means that Optimus has to have all those sub skills to understand all the driving aspects, which it would have because Tesla
Yeah.
trained the hell out of it. Like that doesn't mean that somebody else's. I mean, maybe at some level of what we call AGI, the thing is inherently capable of understanding just the raw physics of the world. But don't forget, I mean, even as humans, we are learning through experience. We don't go through an intersection on day one, never seen an intersection before.
Right.
We go through an intersection after repeated uh, visual exposure to it before we're a driver. Then we learn it through our adults that help us get through it as adolescents, learning how to navigate those things. I mean, sure, as humans, we have some general intelligence to know, uh, if I jump off a cliff, I'm going to hurt myself, right? It's kind of built in, but we don't necessarily understand all the dynamics of these more complex human-built worlds until we somewhat experience them.
So you mentioned that these experts can be thought of skills, right? And if we talk about Optimus specifically, there's thousands of skills I think that we would like Optimus to be able to learn.
Yeah.
So talk to us a little bit about, like, for example, could Tesla train Optimus to do or master a human task? And let's just pick a simple one, like loading and unloading a dishwasher,
Hmm.
without actually, like, entirely in simulation, without it ever touching the real thing.
Yes.
Is
Yes.
that possible?
Yes, I think that is definitely possible because I think it probably starts with some recorded. I mean, look, at the end extent, you can imagine that you don't need any data to train it because it's just a physics model, right? It's pure
Yeah.
physics model. But then you have to understand the purpose and so forth. Like what is the dishwasher? Why are you doing these things? Just like a human, like you might find one dish in the sink and you make a decision to wash the one dish and not put it in the dishwasher because the dishwasher is actually running and you want the dish to be put away. So you make kind of like this decision. But yeah, I mean, at some kind of endpoint of this intelligence, you don't really need much in terms of training data. But I think you can also back that up to the point where I think if you just watch other humans sort of on the imitation side doing actions, you can have Optimus learn from those actions. And that's why I think some of the training data for Optimus is augmented. Like with Tesla, the cool thing is we have this fleet. We have this massive fleet, and so we've collected like data for driving. Optimus, we have this kind of data hole, which we talked about earlier. Like, where is that data? We have this large beta program, probably just video of real world actions by humans will teach can be used in our total training pipeline that we talked about to allow Optimus to learn those skills and build them as expert blocks in its architecture. Yeah.
Is you think about how humans learn as kids, right? We engage in play, and we build our physics model by playing, interacting with the world, learning about physics, right? Basically, is that essentially what we also need to do with Optimus? Is and the related question, I guess, when we see these Chinese bot makers, right? The bots seem to be doing silly things like dancing or
Mhm,
playing some sports, jumping
mhm,
around,
mhm.
and it's kind of like, well, that's not real work. But is the purpose of that perhaps to teach the bot physics?
Well, I mean, I don't. I mean, in that particular example, I think it's a little bit more demonstrating that the bot can abide by physics.
No.
It's a little bit more like, okay, this bot can maintain balance and do these intricate skills that, while we wouldn't necessarily ask our bot to dance because that's exciting to us, or maybe it is, it's some weird home environment thing that you want to do, teacher, hey bot, teach my kid to dance. Okay, great. That's a good use case. But
Yep.
loading a dishwasher is probably more relevant and a lot more boring. I think those are really demonstrations of it. I don't necessarily know that what's happening here is that they're just learning from raw physics. Like I don't know what their so-called training process or pipeline looks like. I think a lot of those things are a little bit more demo than reality, to be fair. I mean, that's the thing about what you're going to see with Optimus is it's going to feel like it's going to sound a little bit pro Tesla here, but I feel like Optimus is a real project, and a lot of these other things are a little bit more like science projects where they're good at demo and they're good at the demo is for the next raise the next round of financing and things that are more involved in like getting you to get there, whereas Tesla can just dig in and get there. It's got resources and brain power to just go off and build this thing first principles. And then, people say, oh, I saw this latest Optimus video. It looks like it took 3 steps backwards. Yeah, so what? I mean, it's not really that relevant. If you saw something that was 5 steps ahead of it in the previous generation of videos, you can be sure that they know how to get there because they were already there. So yeah, I don't really know the answer to your question about like what that proves about those systems understanding of physics at that level. I don't know the answer. Here we are in the last slide of the presentation. We're talking about really getting out to the device itself, meaning whether it's Optimus or FSD, and dealing with the inference framework, right? This is where all the action occurs, where we're actually taking in data, running them through models, and outputting controls, right? So sensor data comes in, if you will, on the left side and outputs controls. And you can see that in the case of FSD, we know what those things are: steering angle, accelerator, braking, and I'll tell you why speaker ends up in the list here in a second. And then in case of Optimus, we have arms, hands, legs, feet. But what's different about this than the normal stack is I'm adding a very, very different and important element, which I call the interactivity and reasoning AI here. So if you think about today in FSD, what does it do? It takes a sensor input, it drives the car, it doesn't ask you any questions, it doesn't interact much with you at all, other than supervising your attention, and complaining if you're not in attention, at least for supervised FSD. And so really it's just the action AI happening, right? It's just the stuff that's basically for driving. But the full reality of this is that we're going to have ultimately integrated in vehicle, certainly on Optimus, a whole kind of like grok system, for lack of better definition. In fact, it will be. It certainly will be technology that comes from XAI, and it will be used for human to device interactivity, meaning like we'll be able to speak to it and ask it to do certain things, and of course, its interface back to us will be speech. So, and then in the middle, there's this reasoning component, which we could largely think of as like an LM for lack of, complete definition. And so if you think about it, how does that manifest itself in a car? Well, we've talked about this many a times, and lots of people have talked about this. Is that we're going to be able, our principal interface to robotaxi, or frankly, our own FSD, will be talking to the thing, and we'll tell it, oh, how many minutes to the airport? Oh, and it'll respond, 37 minutes. Well, what route are you taking? Well, I'm going up the 101. Well, how about you take 280? Well, that'll take 42 minutes. Okay, I'd rather take 280. Would you like to take 280 all the time? Yes, I would. So okay, I'll remember that for you. That kind of system, which is interacting with you, the human,
Will,
and
will
and
that
then doing this.
will that system, Phil, be able to explain to you the actions taken by the action AI?
It could. It could. It's hard to get out of that box how the decisions are made, to be fair.
Yeah.
So I'd rather think of it as the best way to think of it for me is the arrow that runs upward, which is the interactive and reasoning AI is instructing through some context or preference the action AI to do things differently. Now, in the case of my example where I was talking about going to the airport and taking a different route, that's actually kind of jumping out to the routing block. And then that thing is instructing the action AI where to go. But you can imagine, you might say to the action AI, don't park here, go to a corner spot. Oh, you want to go to the corner spot? Yeah, the one on the left. Okay, that one. Gotcha. Do you want me to always park in corner spots? I do. Or, please always go to the top level of every parking garage or
Yeah.
something, whatever. So you're able to both interact in real time with the what I'm calling the device, in this case FSD, and then you're able to potentially have that thing store that as a set of, let's call it for better definition, uh, preferences of what you want. Now, obviously, that's how Optimus is going to deal with us. It's going to, we're going to talk to it. It's going to respond to us, and it's going to do the things we ask it to do, and that's therefore the direct arrow from the interactive reasoning AI into the action AI. Now, this stuff is all happening on the vehicle or in Optimus itself, and it's happening on Tesla's AI 4 or AI 5 chips, which I kind of show in my little chip diagrams below. But the point I'm trying to make here is that we have to zoom out a bit when we think about the inference frameworks of these things, and this is where, if you look at this, you see an incredible unifying architecture, right? It's very clear that you take a multitude of different sensors, you layer them in some uniform data set, which we talked about earlier. You send them both to the action AI and potentially to and the reasoning AI. In the case I've shown here, I'm showing that microphone data would go to the interactivity reasoning AI. And why would it do that? Because it has to listen to what we're asking it to do. So it's going to take in the audio signal. But that might also infer, that must be data that the action AI use, for instance, emergency vehicle sirens, to tell it to avoid, or that emergency vehicles coming, and to be aware of that. And that has nothing to do with the reasoning side, right? It's just what I'm talking about is you've got a set of sensors, and some sensors get pushed directly in one place, and some sensors get pushed in another place, and some sensors get pushed in both places, right? And you could see in some complete example of this, they may be inputs to both sides of the system, and then these two systems are interacting. The action AI and the interactivity AI is interacting. Right now, I'm just showing one way. You brought up the example of going the other way, and then the outputs are the controls we talked about earlier, right? So we know that FSD is largely a picture of the action AI today, but not so much the reasoning. I mean, people say, "Oh, well, the Grok is in my car." Yeah, but it's not really controlling or interacting with your car. It's like there's no interaction between the Grok is just an app, and in fact, it's not even, the inference isn't local, right? It's basically just going to the cloud. So this all has to happen locally, or ostensibly locally, because the stuff all happens necessarily in real time. So this is the output of the whole system, in a sense, right? And you can see that there's a lot of common elements between what is FSD and what is Optimus, and you could see that it's very clear to me that Tesla will have a almost identical architecture.
It's interesting, isn't it? What we're talking about here is an operating system for the physical world,
Yeah, yeah, that's it.
ultimately, right?
Yeah, it is, because you've got. I mean, you could actually see a blend of these two gray blocks here. The action and interactivity stuff could blend into one thing, but I logically think that, for the sake of what's happening at Tesla, they're creating this vision based, operate action type of AI. That's what FSD is. That's what Optimus, when it moves. And then XAI, of course, is working on the component to do, they've got an AI that does speech to text. They've got an AI that does reasoning, call that the LLM. And then they've got a text to speech, which is the output of the reasoning thing. Now Optimus wants to speak back to us. Well, how's it going to do that? Well, it's going to go through a text to speech AI. And of course, if you've ever used, Grok on your phone to talk to it, that's essentially what we're talking about.
Do you think, Phil, that we evolved to sensing or using spectral data, right? Not just visible light, but chemical composition of things, where that's a data input into the system?
Geez, I don't know. I mean, any type of really I mean, just at some level, it's just sensor data, right? I think.
Yeah.
I mean, it's not. It's just a matter of like, what are those data formats and how do they inform the training of the system? So I can imagine, things that, like, I mean, just even in one of my documents on FSD, I talk a lot about the input data for the cameras, and I'm saying to folks is that it's not the kind of images we're seeing. It's a very different type of. That's why Elon always says photon to controls, because he's actually talking about the cameras recording photon saturations through these different filters, the rawest of raw levels, and that's the input to the system. It's not images that you and I, it hasn't gone through an image processor resident on the device to create that beautiful image that you and I see. It's kind of the raw data, and in that regard, it could be in different spectrum. It could be infrared, or or various types of different types of perception,
Yeah.
a sensor perception stuff. So
And then, Phil, the other question I have for you regarding this is data that's being collected on the ground at kind of eye level.
yeah,
How important do you think it might be to add another layer, let's say a bird's eye view of the world on top of this, if that was possible, let's say with drones or satellites? Is that something too that would be, I mean, it seems like it would be of benefit, right, to the model. You'd have a more expansive view of everything around you, not just what you
yeah,
can
sure,
see. You can kind of see, in this case, around corners
sure.
effectively.
Yeah, sure. I mean, that's a very good example. There is, the see around corners thing. I mean, right now we think of these things as these objects that have agency, that have sensors that are. I mean, let's make a simpler example out of it. There's no doubt in my mind that the robotaxi network of the future and the near future will include the aggregate data from all vehicles.
Yeah,
So seeing around the corner isn't so much seeing around the corner as it is just using the sensors from the vehicle in front of us.
right.
And it may not be using the sensor data in its extreme density, but it may be using the outcomes of that. And so my document on, data in a city, I talk a lot about, like, what I expect to happen is the vehicle as an agent would collect the various information and would be given orders as to what it wants to do at inference. And some of those orders would be, obviously, drive the vehicle safely and correctly, but other orders might be, look for graffiti on buildings and look for this particular tag style, and then, or look for this type of dog because there's a missing dog in the city, right? And once the local inference on vehicle 6744 sees that dog, it then transmits that as an outcome to the cloud,
Hmm.
and then it gets dispersed back to the vehicle saying, okay, now we can see this object and now we need to track it through the city. Or, densities of, like, we see instantaneous densities of areas with people or cars that either impede or create, opportunity for robotaxi to be more, you know at the spot of the individuals that are, the highest density individual, like people leaving a baseball game or something like that. So the way I see it is that you can certainly, unlike humans, which is not, I mean, we do this in a different way as humans, but I wrote an article back about this thing called the Optimus network, and it kind of leans heavily in this, where what I'm talking about is that Optimus isn't this thing that we see as a single object. It's a network of things, and the network effect gives it much greater power and intelligence. And there's all sorts of issues with that, about, it can't see in our house, my house, or your house, and then transmit that type of outcome data to the system at large. It has to, there's a lot of privacy and information restrictions, but certainly, like, robotaxi in a city, as a fleet system, can accumulate information. And that's just, by the way, kind of just talking about, what makes it possible, CERN, is that you can't what you really can't do is, you can't take all raw data and send it to the cloud, right? It's just too dense. It's too You need extreme. You need local processing. You need edge inference. Years ago we just say it's local processing, right? We need well, and what we're doing is, essentially, what we're saying is, by doing local processing or inference, we're just compressing the data. We're
Yeah.
just taking raw sensor data and building meaning out of it. And sometimes meaning is what the system instructed us to look for, right? So to your point, you certainly could use overhead drone sensor data that's interacting, back to the cloud system to say, okay, I see emergent problems in the city where there are no robotaxis at the moment, right? Regardless of the ground density, and it makes a lot of sense at some point. I think
Yeah.
what it ultimately amounts to is it's just an architecture. It's just an architecture of the system, and it leans heavily on edge inference, which absolutely has to occur. And Tesla has such a beautiful place here because I mean it's no mistake why Elon is talking up AI 6 while AI 5 is not even out. People might say, well, you know what? Why do I need AI 5 if the car will drive itself well with AI 4? Well, first off, the car can't do all the stuff in this box with AI 4. It can't do all that other interactivity stuff. Probably doesn't have the bandwidth headroom to do that. But then you start thinking about the other use cases of inference beyond the box itself.
Mhm. Yep.
As I point out in that data article, and I start to say, well, wait a minute, you're not just robotaxi isn't just perceiving the driving environment for the purpose of driving; it's perceiving the cityscape, everything there is to perceive, and can answer insane questions like how many visitors are in the city today and where do they come from, because it's got a pin on them from the last time they've been there, or how many new visitors are in the city today, how many are going to this trade show versus that trade show without ever asking the trade show,
Yep.
that type of stuff. Yeah.
It's fascinating, isn't it? It's almost as though Tesla's vehicles and robots become sort of sensory organs in this like growing planetary intelligence, right?
Yeah, I
It's
mean,
this one collective intelligence.
abs- uh,
Um,
absolutely the endpoint. Yeah. No, I mean,
yeah,
it's fascinating to think about that, but I think, in some ways it's far off, and in other ways it's not very far off at all,
right.
because the way we're going to see that first leak into the system is through a collective intelligence through robotaxi. I guarantee that'll be the first instance of it where Tesla and team are using some other data in the system to help robotaxi be the most efficient operator of a rideshare service. Right? That's sort of like, you know, um, I don't know, table stakes kind
Yes.
of I mean, it doesn't even have to be. You be certain that Uber's doing some of that today. I mean, obviously, surge pricing is based on
Yeah.
on that kind of thing alone. This aggregation of data that's happening at the data center. But what Tesla has is the ability that the edge device is a thinking device, and then that it can actually do, this inference framework can do inference way beyond just controlling the vehicle,
Hmm.
way beyond just controlling Optimus. It could be part of just using it as a network device to to uh, bring in general sensor data and distribute general intelligence across the fleet. And that could be distributed 100% across the fleet, um, or it could be distributed to local subfleets of Optimus bots, or robo taxis where something in the environment is important, if
Yeah.
that makes sense. Yeah.
Well, Phil, I think you and I could talk for hours about this topic.
We could.
Um, we probably should wrap it up there before Herbert
That
gets
sounds good.
too upset with me for doing a 3-hour video with you.
Yeah, yeah,
Right.
yeah, yeah,
If people want to read more from Phil, he's on X. So many great articles that Phil has written, and I know that there's a few more on the drawing board. So
yeah. Some good stuff coming.
yeah, Phil, really appreciate you coming to chat with us today,
Sure.
and
Fun.
I look forward to our next discussion. Although I'm not sure if it'll be on the Cernbert channel.
Yeah, you got to be. Herbert might regret the monster he's created here.
That's right. That's right. I think he's going to pull the plug on the monster next week.
Yeah, exactly. All right. Well, you have a good weekend, and everyone seeing this, have a great weekend.
Thank you, Phil. Take care.
All right.
I've created a website that is the most comprehensive resource for the Tesla investor. Please check it out. Simply go to my website at herbertong.com.